If H is a subgroup of a finite group G, then for all A comma B belongs to G, this order of AH is equal to order of H. And the next one is any two cosets are either identical or disjoint. That means identical means these two are equal. Disjoint means there is no common element. That means that is empty. So let us prove the first one. Since AH is equal to set of all AH such that H belongs to H. That means we take an element A from G and multiply with all the elements of H. Then order of AH always less than or equal to order of H, because we multiply the elements of H only. So the elements will not exceed order of H. What is our aim? Our aim is to prove order of AH is equal to order of H. That means we have it to omit or eliminate this less than. So if condition, suppose it is less than, what will be the result? Suppose order of AH is strictly less than order of H, then there exist at least two elements AHI and AHJ belongs to AH, such that AHI is equal to AHJ. In a set we will not count two elements. In a set we will not count two identical elements. So if it is strictly less than means there will be two identical elements. There will be two identical, because AH is what? AH is we take an element A from G and multiply with all the elements. So we can get the same only. Suppose this is less than means in this AH there will be two identical elements. If two elements are identical, what is the answer? AH is equal to AHJ means this HI and HJ always belongs to capital H only. This belongs to capital H only. And AHI is equal to AHJ implies we can multiply or operate with A inverse. Left operation, that is A inverse into AHI is equal to A inverse into AHJ. So A and A cancel, you can get HI is equal to HJ. But H is a set and its order is fixed. Then there will not two elements identical in H. Therefore it is a contradiction. That means HI is equal to H is a contradiction. That means our assumption is wrong. That is modulus of order. Modulus means order only. Order of AH strictly less than order of H is not possible. Therefore order of AH is equal to H only. What is the next one? Next one is either identical or disjoint. Suppose you take it is not empty. That means there will be a common element. That common element is we taken as C. C is equal to a common element of AH and BH. So what is the element of the form AH? An element A multiply or operating with an element of H. So any element of AH is of the form AHI and C is equal to BHJ. But these are belongs to the LHS are same, correct? C equal to AHI, C is equal to BHJ. That means AHI is equal to BHJ. So operating with HI inverse, that is A equal to BHI inverse. The H element is in the right position, so you should operate with the right position only. So textbook it is mistake. That is mistake. You write here the elements is in the right position, so the elements should be in the right position. So A is equal to BHI inverse. So you take this is equation number 1. Similarly, the same way we can prove B equal to AHI HJ inverse. So now you take an element from AH. X is equal to AH. Once again same procedure. What is AH form? Element of AH form as X is equal to A into H and some H belongs to H. So instead of A, already we can put the value of A, that is BHJ, HI inverse, we can substitute for the value of A. So that is equal to, X is equal to BHJ, HI inverse H. Since HI inverse and H belongs to H is a subgroup, therefore it is closed. That means operating with these three elements, the result will be also belongs to H. That is HJ, HI inverse H belongs to H. That means what? This is fully belongs to H. This is fully belongs to H. So some B into H, some B into H. B into H means X belongs to BH. Therefore X belongs to BH. Already X is taken from AH. Now that same X belongs to BH implies AH is a contained or subset of BH. Now you take the another element BH. Y belongs to BH. That is also in the form Y is equal to BH and H belongs to H. Instead of B can substitute the value. That is equal to B value is already we derived as AHI HJ inverse. Now HI HJ inverse and this H, all these three elements and its product value belongs to H. That means this Y is of the form Y into some H element. Some Y equal to A into some H element. That means this AHI HJ inverse H belongs to AH. That means Y is taken from BH. Now it is belongs to AH means BH is contained in AH. That means from these two equations 2 and 3 already AH is contained in BH. Now BH is contained in AH means AH is equal to BH. Two sets are equal if and only if A is contained in B and B is contained in A. That is a rule. So by this rule we can prove this AH is equal to BH. So this is the theorem.